Hello everyone and welcome to our YouTube channel. We have been working on a few videos on ML models and how we can create ML models. And in this video, we'll be looking at the real model based on real data set, and which is it's a classification model that we'll be studying. And the data set that we'll be using is MNIST image data set. So first of all, let me just give you an example. This is a MNIST data set. So as you can see, it's a handwritten number data set from 0 to 9. So you can see the images are quite blurred. That's because the resolution is not very high. And it's something like 4. We can easily make out 4, 8, and 7 from these images. So what we'll do is we'll feed these images to the computer, and the computer will recognize the patterns. So how it will do that? It will split the image into sections of 28 and 28. So 28 by 28, 784. So it will split it into these small parts, and then each cell will have some value depending on the intensity of that cell. Intensity, what basically I mean is either it's black means 0, or it's some shade of white, then it will have some value of, let's say, 0.5, 0.8, something like that. So as you can see, most of it is 0 because most of it is black, but wherever it is white, where it's completely white, it's 1. Where it's grayish, it's 0.8, 0.2, 0.3, and so on. So in this way, the computer can segregate. So like, not exactly segregate, split the image into multiple cells and try to divide the image in form of data. Because the computer only understands data, it does not understand the image or whatever we feed to it. It only takes data, it only understands data. So let's look at the code of this program. So I am currently connected to a HPC Paramrudra, and I am inside the GPU node of that HPC. This is the program that I have here. So a lot of imports compared to our previous videos. There's nothing to worry about. It's nothing to get overwhelmed because there's nothing too complex. So import OS, that's for directory controlling. So whenever I need to, let's say, save a file in some other directory, or take something like retrieve a file from some other directory, OS is required, or create a new directory. So OS module is required for making changes in the directories or creating files, etc., etc. Torch is very simple. Torch is required for the model creation. Torch.nn is for the that's the module for model creation. And then data loader. So it's for loading up the data sets so that they can be fed to the model for training. Optimizers, yeah, pretty common. So torch vision. Torch vision is something new. Torch vision is basically, you can think of it like giving the computer eyes, but not exactly giving it eyes. We can just visualize it like that. We are giving it eyes. So whenever we are dealing with something visual, whenever we need a visual classification, because we require the computer to use some type of visual device, we'll need to use torch vision in that program. And all of these are subsidiaries of that. Matplotlib and all we need for the final, and we need that in the end to create the PDF of the output data as I want to do. It's not a mandatory, you can skip all of these. And lastly, with the metrics, so this is F1 score is something that is it's like a performance score for ML models. So the better it is, the better the model in that field. Now let's get to the program. Pretty standard. Device equals to torch, so it's basically setting the device that I want to use for my program for model training. And next is it will check if the GPU is available, move to GPU. If the GPU is not available, we'll use the CPU. Next is train set. So now I'm defining the sets. So training set, here's torch vision dot datasets dot mnist. So torch vision has the datasets as well, and torch vision dot dataset dot mnist. So that's the, we are referencing the mnist dataset, and in that I'm just going to /data. So that's the directory inside of the mnist. If it is available, sorry, train is equal to true, that means we'll use this data set for training. If it is available, then no need to download, and if it is not available, it will automatically download this data set. You don't need to download it separately. Next is valid set. So valid set is basically for validation. When we need some data for training and we use a part of that data. So MNIST is a data set of 60,000 images. 50,000 we use for training, 10,000 we use for testing. So validation set is basically for testing and all of that. That is what generates the loss and the F1 scores. So transform to tensors, it's very simple. We are just transforming these data sets to tensors because tensor is what the model will accept. And now we are setting up the batch sizes. So what is batch sizes? Batch sizes is how many images I want, how many inputs I want to send at a single time. That is what a batch size means. And yeah, that is what a batch size means. So batch size of 64 means 64 images at a time. So according to your, according to the system that you're working on, according to your hardware capabilities, you can adjust the batch size, but keep it in the power of 2 because that's favorable for computers. And print, so that's just printing the batch size that we are using. Train loader. So basically the data loader that we used before, now we are using that. So so this is what will go inside the train loader. That will what will go inside the model for training. Training set is defining the set, and here we are using that training set and batch size. So it will split the training set into these batch sizes and submit it to the model for training. And shuffle is equal to true, so that means it will shuffle the sets so that there is no kind of like if I were to give it simply and enter it simply, then it will be like 0, 1, 2, 3. But shuffling will mix up the patterns, so it will make the computer, make the model more better trained. It will better train the model, and it will better train the model, and there will be less inaccuracies. Now it's for model creation. Finally, we reached there. And pretty simple, nn.linear, we are creating the linear layer, and when we have used input size, so input size is 128 by 28 because we are splitting the image into 28 sections by 28 sections, and 512 is the output. So if you remember in the previous video of the classification, we had some input and we were splitting those input into multiple outputs. That is the same thing that we were doing here. We are doing here. We are taking 700 something outputs and we are splitting them to 512 input and splitting them to 512. And that's the activation layer. So that's what introduces the exponentials. We have another linear layer, and since 512 is the output from the previous one, so input here will also be 512. And 512 will be the output of this one as well. So linear, just to be clear, linear basically means I'm using a linear equation. So linear equation like y is equal to x plus 3, y is equal to some ax plus b, it is of that type, and I are using that here. And ReLU layer is for exponentials or non-linearity. So like sine, cos, e to the power x or something like that. And finally, that's the final layer, 512, and it will combine it into 10 classes. So like 0 to 9. So I have 10 classes based on that. Okay. It will create the model. So if it's just defining the layers, and then model is equal to nn sequential, and I'll send the model to device. So this is for the loss and optimizer. We discussed that in the previous video as well. Loss function, cross entropy, and optimizer. This time we are using the Atom optimizer. Nothing too serious. And this is just, we are creating the a function to get the accuracy per batch size. So I'll train the model, predict, and get the based on the loss, we'll get the accuracy of the model, and we'll keep training. So this is for the training, defining a function for training the model. Loss equals to 0. I'm just defining variables, and by true by prediction. Yeah, for x and y in train loader, we x to y, y to device, output equals to model x. So we are just taking the output based on the what is model is giving, model dot train. Whatever model is giving for x, we are storing that as the output, and then we are optimizing the parameters based on the model output and based on the loss that a model is generating, basically the error value. And this is after the training is completed, we have the validation set. So it will validate how much after training completion, how much is the loss, how accurate is the model, and yeah, basically it will give us all the scores of the model, how good it is, and if it needs any more updates to perform better. So for this I am using epochs 5, since I have a very large data set, and it will take a lot of time if I take a lot of very long epochs. So PDF file name. So why I am creating this, I'll tell you after the output. So that would be something you need to see, and all of this is for the training output. So for the all of this is for the PDF. No, sorry, this is for the we are training here now for epochs in range epochs. So epochs is 5, so it will run for 0 to 4. Train loss, train ACC, and train F1. So all of these are for the variables that these will return. So if you look at def train, loss, accuracy, and F1 is what training will return. So train loss, train accuracy, and train F1 is what we are getting here, and we are just printing those values. So it's kind of like a log report that I have created here, and I'm training the model every time this loop runs. And finally, here is the PDF creation part. So basically I am testing for 5 random digits from the validation set. I'm testing for 5 random digits set I and 4. So basically 0 to 3, 4 values I'm testing for that in the valid, using the valid set, not the training set. We're testing using the valid set. And then I'm just plotting the images and what the system predicts for that. So what the actual image is and what the system predicts for that, and I'm saving it in a PDF so that it's easier to access. Okay, so let's see the program running. Before we run the program, we'll need to load the module Miniconda that's required for the HPC I'm working on, and then I'll need to activate the environment, which is Mac College, where I have all the required. We have all the required modules is pre-installed. So let's clear it, and then I can do Python 3, D3, UI. Yeah. Now the program will take some time because it's a heavy program. Plus I'm also using GPU for this. So I expect about a minute or two. It will take a minute or two to finish compiling. See, the delay that is happening is because the CPU is sending all of the data to the GPU, because I have specified that I want to use GPU for this program. That is why all of this delay is happening. If I were to use the CPU, it would have been much more responsive. Program would have been much more responsive. And that is also why you need to take care when you are using GPU and when you should use the CPU for any type of program. Now we finally saw some results, and now it will print the tensor. So this is the tensor. And what exactly is this? It's basically, if you see 1, 2, 3, 4, 5, 6, so it's 28 values, and there are 28 of these. So it's splitting in 28 by 28. Batch size is 64, and now the epoch is starting for training. And all these numbers, like I previously explained in the PPT, these numbers mean the intensity of white color in that particular cell. They signify the intensity. Oh, so we're now seeing some outputs. So epoch 1, we had a loss of 209. Accuracy was 0.9, and F1 score was 0.9. And as you can see, after in the first epoch only, the accuracy was very high, 93%. That's really good, but the loss was also very high. But the loss was also very high. So as the epochs go on, loss decreases and accuracy also increases. But at the last stage, you can see it reaches a diminishing point. So that is also something you need to keep in mind. If the epochs is too high, then the model will get overfitted and the accuracy will start to decrease. That's why you need to find a middle ground where you are getting the best performance. So it has generated a PDF and it's stored in scripts for presentation / output.pdf. And time taken for model training is 74 seconds. So let's move to that and see what the output actually is. Yeah, so output that we have got is epoch 1, train loss, and yeah. So here are the actual outputs. So prediction 7, true label 7. So prediction, the model predicted the value to be 7, and the actual value was also 7. This is the image that was fed for testing. Second, it predicted 2 true. It predicted 2 and the actual value was also 2. It predicted 1, actual value is also 1, so it's kind of it's a slanting one, but it is 1. And 4 also it predicted correctly. So the model is giving right predictions for this for the set that we tested it on. So in this way you can create more classification models using real data sets and use them for use them to solve real problems. Apply the AI models to solve real problems and extend it in more fields of study as well. So that is it for this video. Thank you for watching.